All right, systems of equations, two situations at the same time. We're looking for that point that makes them both true, that satisfies both conditions or equations. Yesterday, we looked at graphing, which is a nice visual presentation way to find a solution. It also kind of gives us a nice, well, a visual idea of what it is we're talking about, you know. But today we start with our algebraic techniques. That is, we're going to play around with the equations and manipulate the numbers and stuff so we can arrive at a solution to these two equations at the same time. We've actually been doing that already. All right, time out. Kitty does want to go outside. Let her in. We actually did this a while back. Right? Remember our perimeter equation for a rectangle, twice the width plus twice the length. And maybe we got a problem that said we know the total perimeter was 200 feet. Well, so somehow 200 feet was twice the width plus twice the length. And then we had a relationship between the width and the length. Something like the length equals 3 times the width, or the width plus 5, or something like that, you know? There's a system of equations. We have this initial condition. We know the perimeter formula. And then we have this second condition, right? Second equation. We didn't talk about it as a system. We just kind of said, oh, that means I can take this and plug it in instead of the length. We substituted an expression from this equation into the other equation. That allowed us to write a single equation that only had one variable in it. And that's exactly what we're doing today. This is a substitution. It's an example of the substitution method. Now from here, then we solved it and said, okay, 8W, so the width must be 25 feet. And from that, we figure out the length. 3 times that would have been 75 feet. So we still want those numbers, right? X and Y, point, right? So that's my introduction, basically, to say, we've already done this. So now we're going to just look at more variations of the kinds of equations that we're going to combine and then rearrange so that we get one of them that kind of says one of the variables equals all this other stuff. And then we're going to plug it in over there in the other equation. All right, so here goes. Get rid of that. So without any context to start, right, we're just going to look at a bunch of equations. So to begin with, here's one I might call an easy one. Very similar, actually, in terms of being easy, I'd say, to that first example. Notice no graph anymore. All right, not for a while again until we come back around to review, I suppose. Okay, here's a system. Actually has one in standard form and one in the MX plus B. Right, so the goal is, or a technique, solve one equation for one of the variables. All right, so there's the first step. Solve one of the equations for one of the variables, like L equals 3W a minute ago. Well, look at those two. This one is already solved for Y. All right, that's all solved for Y. Y is apparently equal to all of this other stuff. And then we sub the expression and squeeze it in from that equation into the other for that variable. All right, so that's the basic technique for substitution. I need to clean next. So I call this one an easy one because one of them's already solved for one of the variables. You don't have to do any work for the first step. All right, so if y, if I'm going to come up with an expression that solves a point that solves both equations, it's got to make this one true and the relationship in that one true. And so I can take this expression, which is got to be equivalent to y in both equations, and replace that y with that expression. I'm going to substitute this expression from one equation into the other equation. So now, here's my arrow stuff, right? Now I'm going to rewrite, and I'm only going to have x's left. X plus 3x minus 2. That's equals 6. All right? I substituted this in. Now I've solved. So what do I have? 4x minus 2 is 6. Add the 2. 4x equals an 8. Divide by the 4, x equals 2. Stop, make sure you catch up. So, by doing the substitution, I'm able to reduce my system to one equation with only one variable in it. And I can solve for that one variable just like we've been doing for quite a while now. We do always want both points, both values. Right? Often it'll be an XY pair still. We still need to find the X and Y value. Remember, we're looking for a point on that graph. So now I got to plug it back in. If X is 2, pick one or the other. It doesn't matter. Pick one that looks like the easiest one to stick that into. Maybe actually the first one, right? 2 plus Y equals 6. All right, if X is a 2, and I subtract the 2, I get that Y must be 4. There's my solution. And I could plug it into both of them and verify, right? 2 plus 4, yes. Let's see, 3 times 2 is 6, minus 2 is 4. So yeah, this works in the second one also. And verify. Plugging it back into both. That's going to be our process. Get one equation solved for one variable, and then whatever you got on the other side, you're going to put in for the other equation instead of that variable. All right, here goes. All right, leave that up there for a second. And next. All right, step it up a little. All right, I said that first one was the easier one because it was already solved. One of the equations was solved for one of the variables. This is pretty typical. They both are in standard form. So I need to pick one or the other of the equations and solve one of them for one of the variables. So you look at them and you say, well, which one looks like it'd be the easiest to get one of the variables all alone? When I look at this, I say, well, it'd be pretty easy to get the X alone if I move the 3 Y's. Or here I could say it'd be pretty easy to get the Y alone if I move the 4 X's. So I really kind of have two pretty equal choices because it's a nice 1 on both of those, right? A 1X or a 1Y. So just sort of arbitrarily, I'm going to choose the first one and solve it for X. So I'm going to take this one. If I subtract the y's, can I do that without showing you much work? Are you okay with this one is equivalent to that if I subtracted the y's from both sides? I don't know if that's an issue. All right? So I just did a legal thing. I subtracted 3y's from both sides. It's still the same relationship in the equation, right? Balanced. But now this one is solved for x. This expression is supposed to be equivalent to the x value. So now I'm going to take this whole thing, a lot of circles and arrows here, and got to remember, it's always got to go back in the other equation, so you're putting them together. So this whole thing has to go in there instead of that x. Now this time I have this two-term expression for x, and it gets multiplied by 4, so I'm going to need to use parentheses and distribute eventually. So this one turns into 4 times, because my x, negative 3y plus 10. And then don't forget the rest of that equation, right? Plus y equals 18. So there, I solved. Now I substituted. Now I'm going to solve this equation, which only has y's in it. Carefully distributing, right? 4 of these. 4 of those, plus 40, rest of the equation. There we go. All right. Combine some like terms. Negative 12y plus 1 means I have negative 11y's plus 40. I'll subtract the 40 from both sides. Negative 11 equals negative 22. Nice numbers. Whoops, pardon me, don't lose my y here. Dividing by that negative 11, I get y equals 2. Still fits on the board, good. Y equals 2. I still need to figure out what the x value is. So here's where I go back. This is kind of nice. I can use any one of the original equations, or this one is equivalent to the original equation, and it already is solved for x. It would tell me what the x value is if I use this one. All right? Don't need to use the one where it's still all mixed up. So I'm going to take that 2, and there I go over here. All right? 2 is the y, so x equals negative 3 times the 2 plus 10. Negative 6 plus 10, x equals 4. Well, same two numbers as the first example, but switched around, y and x and y. So this is a little more typical than you might say than the easy one. I've called that first one. You have to do a little work to solve one of them for one of the variables. All right? You got enough of that? Here I go. All right. Stay there for it. Yeah. I can do a few more, just very similar level of complication, you might say. So again, neither of them is already solved for one of the variables, so I need to rearrange one of them to solve it for one of the variables. Look at the two equations. I've got 4 different variable spots there. Which one looks like it'd be the easiest or the cleanest, no fractions or something, to solve for that single variable? The fact that there's a 1y up here makes this one my preferred choice. I can subtract the x's from both sides. and solve that first equation for y without it getting too messy. So again, let me subtract the 4x's from both sides and I will get y equals, I'll put the x's first just because we see it there a lot. Doesn't matter, 2 minus 4x would have been fine. All right. I like to show what I'm doing with all my arrows there. Right? So that means y from the first equation is equivalent to all of this. So I'm going to put all of that into the second equation instead of that y value. And again, there's a coefficient out front. I'm going to have to use parentheses and distribute this 2 eventually here. So rewriting the second one, here we go. 3x plus 2 times, here comes the y, minus 4x plus 2 equals, I should get the right number over here. I've seen it all over. People mix up the wrong numbers there. Okay, now I've combined them in a sense, so I have one equation with only one variable. Here with my distributing 3x. I'll call that minus 8x plus 4 equals minus 1. Okay. Combine my x's, negative 5x plus 4. Subtract the 4 from both sides. Negative 5x is negative 5. Divide by the negative 5, I get x is 1. So I've got half of my solution. Only half. Don't forget the other one. So I need to find the y. Well, again, I could use one of the originals, but this one's already solved for y, so I'm going to use this one. Y equals negative 4 times the 1 that we found, that's 2. If y equals a negative 2, squeeze it in over here again. 1, negative 2 would be my ordered pair solution. Substituting from one equation into the other. Okay, here goes. Yeah. I'm just cruising, you always, you should slow me down or stop me. All right, how about, oh, this one, I say, oh, looking for a good one here. Yeah, I rearranged one a little in my head, double check, make sure. Yeah. All right. Here's one that looks different. 2mx plus b shapes, right? Solve one equation for one of the variables. Well, they're both already solved for y. Oh, well, this is supposed to equal y, and this is supposed to equal y. They should equal each other. In a sense, I could say I'm going to put that there, and I just put the two equations end to end. X plus 4 has to equal 4x minus 2. Again, that's kind of the easy one. They're already both set to y and just making them equal to each other, and let's go from there. Huh? So, how about I'll subtract an x from both sides, and add a 2. I divide both sides by 3. Rattle, rattle. I get x is a 2. All right. And I still have to find the y value, ordered pair. So I'm going to plug the two in. I really didn't change any of them but either of them is really pretty easy to use right now. How about that first one? Y equals 2 plus 4. Y equals 6. I plugged my 2 into that first equation. You want to see all my arrows? There we go. Yeah, I think those. Oh, I've got examples here that I copied out of the text. And let's see, how about this one? Similar. Oh no, a fraction. They gave us nice numbers anyway. It's not too bad. Well, but it does involve a little extra work. All right, so this is another one where y already is solved in both of them, so I can just take these two expressions and set them equal to each other. All right, both of them are supposed to be equal to y. Just to show the arrows and stuff, let's just say I'm going to put that one over there. So 3x minus 16 has to equal 1/3 x. All right, so here I have an equation to solve, and it happens to have some fractions in it. If you recall our technique from back in chapter 3, one idea that we used was to multiply everything by a common denominator to make them all bigger so there are no fractions. Excuse me. So if I were to multiply this, both sides by 3, right, still legal. Over here, I get, cancels out just x, right? Here I have to distribute. I get 9x minus, that's a 48. Okay, that wasn't too bad, dealing with a fraction. So, gotta move things around here. I'm gonna move this 1x. I got all the x's over here, so now I'm gonna move the 48. I'm gonna add 48 to both sides. You get 8x and 48. Dividing by 8. You know your math facts, right? 48 divided by 8, 6. Multiplication tables. All right. So now I have my x value, and I need to plug it into one of those up there. Yeah, 6, that's not too bad. Let's try this one, huh? Y equals 1/3 times 6. That's it, right? 1/3 6, y equals 2. All right. So you might run into a fraction sometimes, like that. I think our mom problems are not very complicated. I don't even recall if we have any fractions in the mom section. We'll just see. How about x minus 4y? I forget what the deal is with this example. Let's see. All right. Got to solve for one of the variables. How about this x? Okay. It's got the 1 on it. It makes it cleaner, easier. So if I add 4y to both sides, I'll get x equals 4y minus 4. Okay. And so now I'm going to take this expression for x and plug it in there. Now, -3 times all of that. So here goes, huh? -3 parentheses, 4y minus 4. And don't forget the rest of that equation. 4y equals 0. Okay? Distribute negatives. -12y. Negative times negative is +12 plus the next 4y. That example might have been all about the negative sign, just to be careful, practice that. -12y plus 4y leaves me -8y's, like terms, right? Plus 12. And let's subtract the 12. Oh, I'm going to do a fraction. -8y is -12. Fraction. Right. So let's see. Divide by -8, right? Y is negative divided by negative is 12/8. Reduce the lowest terms. Divide them both by 4s and get 3/2, 3/2. All right, my y value is 3/2. All right, I need to find an x. Well, this one still will work pretty well. Solved for x already. All right. You don't have to do the arrows, but it might help keep things straight. So x equals 4 times 3/2. Maybe 4/1 if you like it looking like that. Minus another 4. Squeeze it in there. So nicely here that some 2's would cancel. So x equals 2 times 3, 6 minus 4. X is a 2. All right, part of it was a fraction. Maybe that was the point of that example too. Put some fractions in there. Just, step at a time, go slow. Remember, how do I deal with a fraction if it shows up? And again, if it shows up, I think our problems are likely to have a nice way to work with it. So it didn't get too messy at the end. We're practicing a technique here, not getting real complicated. Okay. I guess that just stay on the ground. There it went. Rolled away. And here's ones that's kind of mixed up. I mean, there's standard form, that first one. This one's got the x's and y's for some reason in a reverse order. Doesn't really matter. This actually involves kind of a double jump in complication here. I wasn't looking at those, right? Solve one equation for one of the variables. Oh, none of them have just a 1 on it. This example, I know it's going to happen. There's actually a couple things going to go on here. None of them is just a 1x or a 1y. So then I kind of have to say, well, which one would be easiest to solve for one of the variables? Maybe leave a least messy number. Well, if I solve for the x, I'm going to eventually divide by 2. I am going to get a fraction. Or here, if I solve for the y, I divide by the 3, and I get I'm going to get a fraction in here somewhere. And similarly here, if I divided by one of those coefficients to get that variable alone. So I'm going to solve for the x up there. It's like the smallest number to worry about. So I'm going to show some steps here. There it is. All right, so I'm going to add the 3y. both sides. Now I'm going to divide everything by 2. Okay. Well, okay, I have now this expression, which is supposed to be equal to an x. So I have to plug it into the other equation. Long arrow here goes now. All right, so it's going to go all the way into there. All right, here goes. All right, this equation. Minus 12y plus 8 times all of that. Yeah, about as messy as they're going to get. All right? Understand. There's the substitution. This does have some distributing I have to do. All right, so here's the negative 12y. 8. Luckily, here for 8 times this fraction, I can cancel a 2, right? 8 times 3 halves. I'm going to get 4 times 3. I'm going to get 12y. You probably can't see what I did. Maybe I'll do this. Just for this, over here, I did 8 times the 3 halves, right? So here I canceled that, and I got 4. So I got 4 times 3. There's 12. 12y. But it's still 8 times that also. Okay? So I was dealing with a fraction. And nicely, at least the denominator canceled out. All right, combine some like terms. Minus 12y plus 12y. There's no more y's. I get 48 equals 48. Or even if I subtracted 48 from both sides, I could even say I got down to 0 equals 0. That's always true, and there's no variables in there. What does that mean? Anything that made the first equation true was going to make the second equation true. These are the same lines. Or we'd say, remember that other word, dependent. They depend on each other. They're the same lines. When you get this always true, right? It didn't depend on the variables. It's always true. Now, go back. I said it was kind of mixed up to begin with, like hiding the situation. Notice if I was to take every one of these first equation numbers and multiply by 4, I get 8x minus 12y and 48. One was a multiple of the other. One equation was a multiple of the other. They were really just the same equation written slightly different to begin with. So here's an example of what happens when you've got that graph where the 2 lines are the same line, right? Same line, one on top of the other. Same line. 0 equals 0. And then along the way, we had to do a little extra messy work with some fractions. Practice that a bit too. Excuse me. I'm double checking my numbers here. Okay. Oh, here's another one of those. It's a combination of a standard form and a slope intercept. Slope intercept, x plus b. Again, nice thing about this one, it's already solved for y. So I could take this whole expression and plug it into that y. All right, so here you basically rewrite the first equation with the substitution. So 5x minus 3 times all of that stuff, right? That'd be, don't forget you're going to have to distribute. 5/3 x minus 4 equals, don't forget the 2 over there, right? You're still writing that whole equation. All right, I have to distribute 5x. Now the 3's will cancel when I multiply the fractions, so I'm going to get minus 5x. See how that works there? But I still have to do negative 3 times negative 4 is plus 12. Minus minus equals 2. You see it coming? Combine the like terms. The x's cancel each other out. I get 12 equals 2. Wow, there's some new math. Not true. No solution. Parallel lines. No solution. What was that classification word? Describes that one condition. Inconsistent. System. An inconsistent system. There is no solution. These two lines, if I were to take this equation, here you can kind of see it right here. Oh no, that was the other one. If I were to take this equation and solve it for y, I'd get 5/3 x, looks like minus 3/2. It'd be a different y-intercept, but the same slope, 5/3. Same slope, different intercept, parallel lines. So previous example, you get something, boils down to always true with no variables. So that was the dependent, same line. Here we get always false, no variables. So two parallel lines, no solution or inconsistent. So this is how you would algebraically determine that. I think some of your mom problems in this section, 5.2, ask you to determine the number of solutions without graphing it. Huh? Maybe that was even in section 1. How many solutions without even graphing it? Well, you have to make the equations look similar, like mx plus b, so you can compare the slopes. Do they have the same intercept, which means they're the same line, or do they have different intercepts, so they're parallel? Or here we actually, we're using our substitution method. It boils down to either a always true or always false statement. Just by looking at them, right? If I was to take that first equation and solve it, let's say solve it for y. I solved it for y, I'm going to move the x's here for a second. Minus 3y minus 5x plus 2. And if I divide it by the negative 3, negative, negative, I get positive 5/3 x minus 2/3. So comparing this equation here with that second one, I can see they have the same slopes, but different intercepts. So I could just look at the equations and say, oh, they're parallel. If I did all that and it was actually the same equation, well, then it's the same equation. Infinite number of solutions, dependent. So one solution, if you boil down to that one xy pair, infinite number of solutions if it's the same equation, and no solution if you get same slopes but different intercepts. Now, once you get to this point, you can look at the slopes, and if they've got different, well, the other thing to be able to do at that kind of problem, if you're looking at the two equations, if you can determine they have two different slopes, that's all it takes. Two slightly different slopes, they're different lines. They're not even parallel. Slightly different slopes, they got to be different lines. It's going to be one solution. Okay, so Substitution, possible applications. Well, we already did a perimeter type problem, right? Yeah. Here we go. So versions of that perimeter type problem would be good candidates often for substitution method. How about this one? Geraldine has been offered positions by 2 insurance companies. The first company pays a salary of $12,000 plus $100 commission per policy that she sells. Right? And the second company offers her $20,000 plus $50 per policy that she sells. And then the question is, how many would she have to sell to make them to earn the same amount from both? How many would she have to sell? Well, so I need to write 2 equations. I'm hoping we're getting more comfortable with this format, but here's a fixed amount plus a variable amount, depending on the number of policies. This kind of information makes a nice mx plus b equation. So that first one, I could say, let's say y for her total earnings, right, is $100 for every policy she sells plus $12,000. The other company, her earnings would be $50 for every policy she sells, and plus 20,000. But y equals y. Set them equal to each other. They're not on this page here. Hopefully they're not. 100x plus 12,000 has to equal 50x plus 20,000. Okay. How about I'm going to subtract the 12,000 and get 100x equals 50x plus 8,000. If the numbers got really messy, of course, I'll have a calculator. And I'll move these, I'll subtract the 50x. So 50x's are left, has to equal 8,000, and that's 4. I can divide both. Here's my mental math, right? Divide them both by 10 means I drop 1 0, so I have 800 divided by 5. 5 times 800 divided by 5 is 160. Ah, see, I'm glad I thought 160. X equals 160. I was going the wrong way. 5 times 8 instead of 80 divided by 5. 160. So X is, what did that stand for? X was how many policies, right? Probably should back up and say, when you're talking about an application problem, you need to define the variables for yourself. That's like X equal how many policies. Policies and Y equals total earnings. Probably should write that in for yourself. You know, you need to define some variables for a problem. Sometimes mom will tell you, use X for this and use Y for that, or use M for this and use N for that, or something. Gotta read that carefully so you don't mix them up. But otherwise, you were just starting from scratch on your own. You really should just define your variables. So this one just asked how many they had to sell. She had to sell. Only really asked for the X value. I had to sell 160 policies. Now, it might follow up and say, how much did she earn if she sells that? How much would she earn if she sold that many policies? Well, that's plugging this X value back into one of these equations. Right? If I plug 160 in here, I get 160 and two more zeros. Looks like $28,000. She earned 28. All right, squeezed in too much there, but talking through the concept mostly. Hopefully that makes sense. The problem just asked for how many policies. Didn't really ask for the X and the Y, but a problem might ask for the follower. How much was that in earnings? Plug it back in, just like we're doing it, except it's an application. Okay, and well, we got through it, and I see we're just out of time. All right, it's almost exactly here, 10:50. So a perimeter type problem, like I started with, is often a good candidate for the substitution method. The length has some expression, 2W minus 5 or something, and we substituted that in. Here's another example where I got 2mx plus b type equations. That's nice to get to 70 for each other. So that's our substitution method. All of the steps. Tomorrow we look at the last technique where we really kind of do something where we're going to add the two equations together and make one of the variables go away. Eliminate one of the variables. So that's 5.3. And we'll get through that tomorrow. And we've been talking about applications as we go along. So come Thursday? No, what day are we? Come Thursday, we start talking about applications, and we'll be off to a head start. So that's it for today. And give them a try. Don't wait too long before you exercise your own brain. I'll see you tomorrow.
Thank you, Steve.
All right, you're welcome. See you later. Have a good day.
You too.